You guys can start.
Hello, am I audible?
You are audible in the Genie. I don't know about the YouTube link.
Yeah, I think I'm audible now. I can see comments.
Yeah, now it's audible.
Okay. I'll restart. So we will be ensuring the communication protocol between our microcontroller
From
and this.
beginning placing components, maybe.
What?
Start from the placing components, I guess.
Oh, okay. So our first step when we are designing, we are making the schematics is to place the main components. So we have our MCU, we have GPS module, our accelerometer and LoRa module. So for accelerometer, I'm using LIS3 DHTR. For LoRa, we are using SX1276 LoRa module, and for GPS, we are using Max M10S. So that are the main components which we will be having in our transmission part. And also we can see a power part. We have a JST pin and a MCP 1700 voltage regulator. So I will tell its purpose properly in later slides. So these are the main components which will we will be having in our transmission part. So okay, so before moving to the connections, I will explain what net label is. So when we are connecting, when we are wiring every pins directly, then the wiring can become very messy, right? So there are many connections between all these components, and the wires can intercross each other, and it can become very messy. So what we will do is we use something called net label. So net label is like non-physical wires, like in simple terms, I can say it is a non-physical wire. So if I use a net label on my GPIO 5 called I2C SDA, and on my accelerometer's SDA pin also I use a net label with the same name, then essentially they two are connected. Like even if there is no proper wiring from that pin till the accelerometer's SDA pin, it is actually connected if you are using the net label. So that is the purpose of net label. So some of the important net labels which we will be having in our circuit, I have mentioned it in this table. So we will be having our power part, which will be powering all the ICs. Then we have the ground, which act as the ground reference. Then to ensure the communication between different components, like between the microcontroller and the GPS module, we will be having UART protocol. So for UART protocol, we know we need a transmission and receiving line. So we will be having that pins. Then to ensure the communication between our accelerometer and microcontroller, we use SPI protocol. So all the pins which are needed for SPI protocol, we will be having as net label. Then to ensure the connection between the microcontroller and LoRa module, we will be using the communication protocol. Sorry. For the microcontroller and LoRa module, we will be using SPI, and for accelerometer and microcontroller, we will be using I2C protocol. So all the pins which are needed for ensuring this communication protocol will be there. So yeah, that's about net labels. And also I discussed some of the important, we ensured the communication protocol pins. So now, before moving to connections, we will discuss what a pull-up resistor is. So in many parts, you can actually see resistors in our circuits, which are connected to the VCC. And these are called as pull-up resistors. So like before explaining what a pull-up resistor is, like I will make you understand why do we even need a pull-up resistor. So for that example, I'm using this IO0 pin of our microcontroller. So if in normal cases, when we are running our program, this IO0 pin, it should remain high. So whenever our program need to be coded, run and all, we need this IO0 pin to be in high state. And whenever we need to upload our code, like it's called as flashing, right? So whenever we are flashing, we need this IO0 pin to be low. So it's generally on, but when we are flashing, it is low. So why can't we just connect it directly to high with a switch? So whenever we need to flash, we can just turn off the switch, right? And all the other time I can just turn on the switch and it will be directly connected to VCC. Why are we not doing that? And why are we like using a resistor and pulling it to VCC, and we are having a different line which connect our pin to the ground using a switch? So why are we doing so? Why can't we directly connect it? So the answer is floating actually. So I'll explain what a floating pin is. So when we are not connecting any to anything, like in my case, I said we can just use a switch, and whenever we are flashing, we can just turn off the switch. So when we are turning off the switch, actually it is not the pin is not connected to anything. So it is called as it is in a floating condition. So in this floating condition, the pin can actually take noise, like electrical noises from nearby pins. So even if we need it to be in ground, maybe because of some electrical noises, a voltage can be induced there, and like our microcontroller will think it is in a high state. So to avoid this condition, to avoid this floating condition, we are using pull-up resistors. So see here, now I have connected to VCC through a resistor. So whenever the switch is off, we will be connected to high voltage, right? And when we need to flash, we can just turn on that switch. So our pin will be connected to the ground. So the next question is, why do we actually need a resistor there? So if there is no resistor, then what happens is when we turn on the switch, like when we need to connect the pin to the ground, when we turn on the switch, there will be a short circuit between the VCC and ground. So to avoid that short circuit, we need a resistor which pull down the VCC. So that is a pull-up resistor. So in many points, many parts, many pins, you can see the pull-up resistor. So whenever you see a pull-up resistor, you need to understand that it is to avoid a floating condition. Then the next topic is decoupling capacitors, which you need to know when we are connecting, when we are doing the schematics. So in many places, in many power pins, especially, we can see capacitors which is connected to the ground. So why do we need these capacitors? Like actually these capacitors are called as decoupling capacitors. So why do we actually need a decoupling capacitors? So actually in an IC, it doesn't take current at a constant rate, right? Like when we get a signal, we need to have a sudden burst of current. So this switching between this low current and high current, like it can take time if we are taking the current from our actual voltage power source. So instead of waiting for that, the what we actually do is we will be having a capacitor which very close to the power pin of the IC. So this capacitor can like act like a small energy reservoir. So it will store a small amount of electrical charge, and whenever the IC need extra current, it doesn't wait for the power supply. The capacitor will immediately like supply that current. So as we are not waiting for our power supply, the data can be like smooth. Otherwise, if we are waiting for it, the data can be corrupted, and we our circuit like won't work properly. So for that purpose, we are actually using the decoupling capacitors, and they also help to filter electrical noises. So we know in our circuit there will be many noises from the electromagnetic interference, or yeah, like there will be many noises. So to avoid the noises also we can use the capacitor. So capacitor act as a noise filter. And yeah, you can see here I have used a 10 kilo ohm capacitor, uh sorry 100 NF capacitor. And in some places we'll be using 10 UF capacitors. So there will be capacitors which have a high value and a small value. So to filter high frequency noises, we will be using the capacitor with low values, and to filter the low frequency noises, we can actually use high value capacitors. And this high value capacitors is what actually act as a energy reservoir. Like I mentioned the problem, we need a sudden current burst, so we need like a backup power source. Like whenever we need instant current, then this capacitor can actually provide it. So for that purpose, we'll be using high value capacitors. So the two problems which our capacitors, decoupling capacitors is solving is, one is to filter the noise, and the other problem it solves is to act as a tiny backup energy reservoir. Then we have our power part of our circuit. I already said we have JST pin. So this JST pin is actually like a connector. We will be connecting our battery in this position. We will connect our battery's positive positive terminal to the V in of our power regulator, and we need the negative part to act as the ground reference, right? So what is the purpose of this MCP 1700? So like the battery won't be providing a correct voltage, like it can fluctuate, right? But our circuit actually need a correct 3.3 voltage. And to ensure that, we will be using a voltage regulator. So this MCP 1700 will take in the voltage from the battery, and it will always output a constant voltage. So to avoid that fluctuations, we are using a MCP 1700 power regulator. So the next component is accelerometer. So to ensure the communication between our accelerometer and the microcontroller, I already said that we will be using the net labels for establishing the communication protocol. You can see here there is I2C SCL and I2C SDA. So this is for communicating between the microcontroller and our accelerometer. Then we have the power pins. Also, you can see there is a pin called axle_into1. So in our project, what we need is our MCU should be sleeping all the time. Like whenever there is no motion at all, we don't need it to work, right? We need to save the power. So what we need is, when accelerometer detects any motion, we need the ESP32 to wake up. So for that purpose, we are using this axle_into1 pin. So whenever a motion is detected in the accelerometer, this pin will give that message to our microcontroller, and only at that time our microcontroller will wake up. So the axle_into1 pin is serving that purpose. So now this is all the pins which are there on the accelerometer, and to which we will connect. The connections are explained in this slide. Yeah, so from GPS part onwards, Satvik will be explained.
Yeah, I'll be continuing. Hello everyone. Okay, we have seen some of the connections shown already. Now let's quickly look at the ECDA software, then we can continue. So you can type ECDA and get logged in with your account and choose standard edition. And you can create a new project, select a new HTTP standard project, and can name it new project one or whatever you want. And you can save it, and then you'll get a empty schematic. And here is the common library. You can select resistors or capacitors and everything. And here we'll get all other parts in the library part where we can search and place our components. As previously explained, we have seen the main components and I'll place them one by one. So just go to the library and search for them. As you can see, we are using a microcontroller. We are using ESP32. Just search for the ESP32 models and then try to search for the exact model so that you won't get any problem. And here we are using this module. One second, let me type up the. So here you can see I have typed the module I'm going to use and I'll search it and here it is and I'll select it. You can see the diagram and the layout here. You'll place it in middle of the layout and then you'll also search for other parts similarly. I'll also put some other part, for example. So the power regulator, we're using MCP 1700T and I'll search for it. So I'll make sure I look for the exact part. So here, let me copy this. I already have the schematic. So I'll just paste it here. And also I'll just place this. Sorry. Also, if here in the wiring tools, you can see the wiring and also net label. If you haven't watched the session 3, the PCB designing basics, go watch that one. It will be clear. So I'll take a net label for now. I'll place a net label here and I can name it in the properties I'll name it for now VDD underscore 3V3 for the power. And then I'll place the net label here and then I'll copy the net label and I'll place the other net label corresponding to the 3v3 point here. And I'll make sure the name is same so that both are connected. I'll just name it the same one. And I'll use the wiring tool to connect them. So if you use the net labels, these two parts are virtually connected so that there will be no messy wires in the schematic. In the common library, you can find the capacitors. So I'll just show one capacitor for this. So you can name the capacitor value to be as we are, you can see the text 0.1 as we are using for the decoupling capacitors as mentioned, we are using 1 microfarad and then we'll place the ground from the net labels and use a wiring tool and just connect to the VDD and also connect to the ground. So similarly, you will connect all these paths and use the net labels as shown in the slides. We are showing the clear pins. So use the net labels for every pin and every connections. And similarly, you can place the other components as well. So the final schematic must look something like this with all the parts. So here all the modules are mentioned and let's continue with the slides. I'll explain remaining connections. We have looked up to accelerometer and their connections. Let's continue with the GPS module. We'll go into the presentation. Yeah. For the GPS module, we are using MAX M10S00B01 module. This you can type up and get one. And here you can see the connections, and I'll go through one of the connections in detail. So the first pin, the VCC pin, the 8th pin, will connect it to the MOSFET output. I know, I think you must have come across the MOSFET. I'll also explain it in detail in next slide. So it is connected to the power. It is like a switch, I'll explain. And the ground is connected to the common ground for the return paths. And here you can see two important paths, two important pins, TXD and RXD. So TXD and RXD are the transmission and receiver pins, which we are going to connect them to the ESP32. The transmission pin of the GPS is connected to the receiver pin of the ESP32. So it's to send coordinates and receive coordinates. The pins that are connected are 18 and 17. And then another pin named SafePut_N, which is connected to a pull-up resistor 10K ohm value, and then to the power volt. It's usually for rebooting of the GPS part. And there are also other pins which are not needed, the time pulse pin and the reset pin. So there's also a V backup pin. So it's like a backup voltage which is connected to 3.3 volts. It's for to keep backup memory even though the GPS is turned off. So here you can see the ground placed and the safe put for the pull-up resistor. And here we can see decoupling capacitors placed to the VCC. And this part is MOSFET part. I'll explain what is a MOSFET next. So MOSFET, we are using a MOSFET. Why are we using is because so when GPS is powered, the GPS is powered directly to 3.3 voltage. So GPS utilizes battery, so it easily drains the battery. We only want the GPS to work when the motion is detected. So when the motion is detected by the accelerometer, it wakes up the ESP32. Then only the GPS should wake up and send the coordinates. So we are using the MOSFET like a switch, which is controlled by the ESP32, the microcontroller. So whenever ESP32 is turned on, there are three pins in MOSFET: source, drain, and gate. So there are three pins: source, drain, and gate. So drain is connected to ground and source is connected to 3.3 voltage. The gate is controlled by the ESP32. So there are also two types of MOSFETs I'll explain. One is called PMOS. It's P type P channel MOSFET, and another one is NMOS, which is N channel MOSFET. I'll explain the difference. So the switch is controlled by the voltage, right? So some voltage is there at the gate and 3.3 volt is there at the source. So if my voltage is less than 3.3 volt, then the MOSFET will on in PMOS type. If my voltage is greater than the source, then my MOSFET will on in an N channel type MOSFET. So there are two types of MOSFETs. One is P channel type and one is N channel type. It depends on their functions are depend on gate voltage. If my gate voltage is less than source voltage in a P channel type MOSFET, the MOSFET will turn on, which is mentioned here. We are using a P channel MOSFET and the gate pin is high. That is, when the gate pin is high, it is greater than the source. So GPS will be off. So when the gate pin is low, it is less than the source. So GPS will be on. So here you can get the difference between the main difference between PMOS and NMOS is we use P channel type MOSFET to whenever we want to switch power, we use P channel MOSFET. Whenever we switch ground or a low voltage, we use N MOSFET. Here we want to switch power for the GPS. We want to control the power for the GPS, so we are using P channel MOSFET. Okay, then let's continue with the LoRa connections. So the LoRa module is SX1278F43S module. And here you can see the pins. We can see first the ground pin is connected to the common ground, and the VCC is connected to the VDD 3.3 voltage, and also the decoupling capacitors are placed here. And we'll see the next connections also. Here you can see two important pins, SO and SI. For the connection between the ESP32 and LoRa, the communication protocol we are going to use is SPI protocol. We have already seen what is an SPI protocol. So here in this setup, we are using all three different types of communication protocols. Between accelerometer and ESP32, we are using UART protocol. And between LoRa and ESP32, we are using SPI. Sorry, between accelerometer and ESP32, we are using I2C protocol. Between GPS and ESP32, we are using UART protocol. And here we are using SPI protocol. I'll explain in the next slides. So the VCC is connected to 3.3 volt and the ground is connected. So SCK is the clock pin. It's used to configure LoRa according to the ESP32, which is connected to the 12th pin. It makes sure that the ESP32 and LoRa are configured with the same clock. And two pins, SI and SO, also called MOSI and MISO, which are abbreviated as master out, slave in, and master in, slave out. So here the master is ESP32 and the slave is the LoRa module. So SI pin is master out, slave in, so that the ESP32 sends command and the LoRa module receives command through this SI pin. And LoRa module sends the command and ESP32 receives the command through this SO pin. So these pins are used for the communication between them. And NFS is a select chip, which is usually, it makes sure that the ESP32 and the LoRa are connected. And RST is a reset pin. And DIO0 is one of the most important pins. It's an interrupt pin. I'll explain what is an interrupt. Whenever ESP32 sends the data to the LoRa module, so it's configured with clock, right? So interrupt makes sure the ESP32 is interrupted. It stopped for a second and the data is transmitted to the LoRa and transmission is completed, and then it will resume and back, and ESP32 will resume back the operations. That is called interrupt pin. We are connected to the 8th pin, and RF pin of LoRa is connected to the external UFL antenna for the transmission between the transmitter and receiver. These are all the connections. Here you can see all the connections made to connect. The communication connections are connected with the help of 33 ohm resistors. And NSS pin and
Hello?
reset pin are also there.
Am I audible?
And this is a UFL antenna, so that the radio waves are transmitted from LoRa, from transmitter to the receiver. And then we'll see
You're
the final
audible in the
part.
Genie. I
The
don't know
transmitter circuit,
YouTube
the
thing.
schematic must look finally like this. Here we can see the power section with a regulator and the battery holder. And here we can see the ESP32 part. And here we can see the accelerometer as well as LoRa module we have placed here, and also the LoRa module here. So the final schematic
Yeah, I
must look
think I'm
like this
audible
with
now.
all
I
the
can see
connections and all.
comments.
Make sure you,
now it's audible.
when you're making
I'll
yourself
restart.
this one, look at this diagram and make
So,
sure everything is proper.
We will be
at this
using.
point.
We will be ensuring the
And then
communication
we'll finally
protocol
look at the
between our
flow
network
diagram of
controller
our
and
project.
Beginning
So the battery is connected to the regulator,
what?
Start
which
from
is
the placing components,
modulating
I
the
guess.
3.3 voltage.
Oh, okay.
So initially SP32 is in deep sleep. It's in off mode. Whenever the accelerometer detects the moment
So
detected,
our
that
first step
wakes up
when
the
we are
ESP32.
designing, we are making the
So
schematics is to place
ESP32
the
turns
main
on
components.
via MOSFET. So ESP32 sends low output to the MOSFET, which makes the MOSFET turn on. And then GPS acquires the location and sends to the ESP sends coordinates to the LoRa module. and it transmits via LoRa antenna, the radio waves. So ESP32 repeats every 2 minutes, so the clock is configured. Whenever the movement stops, the final GPS coordinates are transmitted, ESP32 turns off, and ESP32 returns to the off mode deep sleep. That's how the project entire it should look like. And this the receiver side schematic, which is another schematics, similar only. You'll place the battery part and the regulator, and also ESP32 and the LoRa module only. It does not, the receiver have only the ESP32 and LoRa module. And the connections between the ESP32 and LoRa module are similar only. Same the VCC connections and DA-0 interrupt connection with the resistor and the decoupling capacitors. This RFL, UFL external antenna also connected. And same NSS and reset pins and MOSI and MISO pins also same. So this ESP32 will just have the LoRa DAO pins and LoRa pins only. No other pins will be connected. All will be marked wrong. And the ground and VDD pins will be there. And this setup and all the decoupling capacitors and will be there. This receiver side is simple enough. So by this we'll complete the schematics of our project. So this is the transmitter schematic, and this is the receiver side schematic. And for the layout part, my teammate will continue. Tejas, you can continue.
Hello everyone. I hope I am visible. I mean audible. Full stress. Okay, this is the PCB we are going to design. This was the the coordinators explained everything very neatly. So this was the schematic part, and this is how the output PCB will look like if you make your layout like this. So first, we need to keep in mind a few things before making the PCB. We need, okay, the thing is, PCB designing is not only about like routing traces to the correct pins and all. It's also that we should reduce the EMI, I mean, electromagnetic interference, so that the noise doesn't like transfer from one signal to the other signal. That is highly dangerous, and we have to avoid that. So we'll see while doing the PCB layout how we'll like adjust to those things. Before that, we'll see the basics of what should we keep in mind. The thing is, first we need a ground plane. In a PCB, there's a top layer, bottom layer, and the ground plane, and so on. So what a ground plane does or benefits us is we don't have to route the grounds, connect every ground to each other and make the PCB like more congested and all. And the second important thing is we can reduce the loop area. What is a loop area? So in any circuit, like if you draw a circuit, like simple circuit, a battery, resistor, that is the load, and again going back to the battery itself. So in that thing, the loop area is the area of the circuit, total circuit, the length into breadth of the rectangle, let's say. So why do we need to reduce the loop area? So the thing is, if we reduce the loop area, the circuit acts like a closed current carrying conductor, and it has magnetic field along its axis. So whenever the current is like switching or fluctuating or changing, that is what a signal is. It always changes. There will be a changing magnetic field, and it produces a changing electric field and causes an electromagnetic wave to radiate. If there is any sensitive part in the circuit, it can affect the signal by when the sensitive part like captures that. So we need to make the loop area very small so that the inductance is reduced a lot and the magnetic field is also not very high that can radiate to a larger distance. Second important thing is when we have the traces that are very congested, you would have noticed that while doing your assignments, that when the traces are congested, we use a trick like using a wire in one layer, going to the other layer and switching to the other layer and connecting the wire to the through hole, or placing another wire, connecting these two wires and go to the top layer and connecting to the SMD. The third important thing is the ground plane is a copper plane, full copper. So whenever we use a wire, it needs a clearance. The wire and the copper plane should have some amount of gap. If the net label of the wire is not the net label of the copper plane, or else they will be like conducted physically and electrically. So we need to rebuild the copper plane, not only because the copper plane can form islands around. I'll show you how an island looks like. And also because there should be some clearance between the traces and wires from this copper plane, so they are not electrically conducted. The fourth and fifth are like the main component should be at the middle. Separate whole PCB into zones so that all the components that have connections closer to this main component come closer together. And the sixth point is avoid EMI. That's an important part. Routing traces is not an issue. It is an issue sometimes, but the main part is avoiding EMI. We won't notice when we do those things, but when we use those PCBs, it will be like a headache. Okay. We'll go directly to EDA. So this is the schematic. Right. These are decoupling capacitors. And I thought of saying, okay, let's start with this. Why? Okay. Aisha explained the decoupling capacitors very well, but I want to ask a question like, why do we have two capacitors in parallel? And one is in nanofarad, other is in microfarad. The reason we need to have a parallel capacitance having one this range and another in this range is a brilliant move. The schematic was made by Aisha and Satvik. So what this does is a larger capacitor can store a larger amount of charge, and when there is a current spike in this VDD, it can provide the voltage, the current directly and not required for the external supply. But this is the external supply, not required to get the current from this end to this. That's a long way. And that's also a problem with that. That is the reason we are using decoupling capacitor. So let's say the VCC, always remember, and even if you use traces, PCB layout or not, current flows in a closed loop. So the VCC of this part will get its power from the VDD of the ESP32 or directly from the regulator, and it goes into this VCC and circulates through the internal circuit, providing current, and then comes out through the ground, and the ground will be connected to the ESP32 ground or to the regulator directly, and it goes out. So whenever there is a current spike in the internal circuit will require more current to flow through the VDD, and at that time there will be a fluctuation based on how much current is needed. Every time it will be a fluctuation, and the VDD part won't be 3.3 volt, it will be a little less than that. We don't want that, and we use decoupling capacitors. So this this will provide the immediate current supply that is needed. It will act as a temporary battery and will provide the immediate current supply. This is a larger capacitor that can store a large amount of charge and supply more current. And why is this small capacitor used for? This is used for the frequency filtering that Aisha had told. So I wanted to show you the thing actually happening here. So whenever VDD is connected here, the capacitor only allows for the capacitor for DC current, the capacitor acts like a open circuit. For the AC current, it flows through this. So whenever the noise is there, the 3.3 volts acts as a DC current, the noise acts as an AC, almost like an AC, and the 3.3 volt does not pass through here, while the noise moves along this path and goes through the ground. This was one thing I wanted to tell. And the JST connection, these are called the headers or connectors. So this is how they look like. You must have seen them somewhere. These are 7 or 9 pins JST connectors. These are wiring tools. These are drawing tools. You must have gone through them in doing the assignments. I hope you know what these are for. If you uncheck them, you won't be able to see them. The drawing tool is gone. I want them. Then the toolbar, we'll use the cross probe when we want. And the second thing I wanted to tell is, if you don't know the part, model number, etc. and all, you just go to fabrication, one-click order parts, and you go there, go to catalog, and if you want a resistor, quick resistor. And these are different types of resistors you want. If you don't know the model number, choose one of these. I want a chip resistor because they are small and space is conserved. And you go inside them and you choose 0805. That is better because most of in the common library you will see 0603, but it won't be available with the manufacturer. Many of them, but 0805 is available. And the resistance, that is what we need. Let's say we want 33 ohms only. Click on this, apply all, and you'll get the chip resistor. What we are using is this one only. So this is an easier method. And if you want to know if this is the actual one you require or not, you can go through this data sheet and then choose the component. If you don't know the model number, how to choose and all. So that is all it is. Then we'll go directly to the PCB design, go to design, convert schematic to PCB. So already there is 4 copper layers. I'll tell why we can do it in 2 layers or 4 layers. In this one, even in 2 layers, it is easier to route them. But I don't want to do that to reduce EMI. I'll tell you why. First, this is how the components are, right? So just place them. This is the ESP32. Okay, the thing is, it is so confusing, so many blue lines. So what we'll do is go to tools, go to net color, go to GN. What we are going to do is, we don't want to see so many blue lines. I want to separate ground and power from other blue lines. So we'll give them some colors. We'll give ground white color. We'll give VDD green color. So you'll see that, okay, these are the connections. What? Okay, we'll keep ground and ground plane, so no need to route them. I won't consider them while placing the components. I want to place components based on these blue lines alone and not green or white. I'll place them here. See, these two needs to be connected here. This is the UR to TX. This is GPS module. Yes, this is GPS module. This is the accelerometer. And the thing is, while placing, you need to see those lines. They should not like cross over the another components lines. You need to see them carefully, rotate them if you want. These two should be connected and it is not like overlapping with others. Fine. And then this should be connected to this. The thing is, sometimes we need to take like to take the choice. If I connect this to this, I won't be able to connect these two traces in the top layer. So what I'll do is I'll use the wire part and connect it with that. 2 is better than 1. So we'll do it at the bottom layer. So what I wanted to do is connect the main parts first so that we don't have to compensate them for smaller parts. So these are the capacitors and resistors we have. The red color you see is different from the white and green. The white and green are for GND VCC. The red is the signal part. So there is no space for this. We have to move these parts and make sure that you don't cut any existing trace lines, that lines that can be possibly be traced out. Sometimes if you lose hope in doing this, it is better if you see the 3D part. Okay, I have done this much. It gives motivation. Like sometimes we need to try to visualize them. Visualize if there will be space enough. If you press space bar, it will rotate. Oh, okay. This should go to SDA. This should go to SCL. There should be space. So all these are the decoupling capacitors we use. So everything is GND and DCC. So how will we know which one should be the one to connect to which component? Because each capacitor has a different value. So we'll see that. Where did I put it? So for that, first save this thing. Go to the sheet, go to design manager. It will have the nets and components part. What we know is that it has, what are the C10, 11, 2, 4, 6, 8, and 9. Where is, oh shit, components part. C2 belongs to MCP. C1 also belongs to MCP. Okay, C1 and C2 over here. C2. And we don't want to go there searching for C2. So what we'll do is click this thing, go to tools, click cross probe. It will directly go to this. MCP should be something. Oh, this is MCP. Sorry. Place the decoupling capacitor close to the pins as much as possible. Then we know, oh, C1 is already there. Yeah. That is not a decoupling capacitor. There's a signal over there. So C4, C6, C8, C9. C4, C4 and C6 are for ESP32. Oh. C4. Now we need to place it over here. How do we do it? Make some space. Okay. The thing is, we won't be able to place another. If we do like this. So I'll do in this way. Okay. C4. Then C10 and what else? C10. C10, 11, 8, 9, 8, 9, 10, 11. C8 is here, C9 is here. This is what is accelerometer. Eight and 9, right? We should place it over here. Fine, then 10 and 11 only left. S6 is Dora. This is only that. Okay. So this is how we do it. We need to keep the board also compact, and also we need to route it. And so there are few things we need to keep in mind while routing, and so that we don't make EMI or noises to spread through signals. First thing we will discuss about is crosstalk. So these two are close, right? The traces also will be close only. So we'll see what a crosstalk is. A crosstalk is when when the neighboring signals have signal bleed. Like one signal is interfering into the signal of the other. This happens when they are placed closely or runs very for a very long distance. So why does that happen? It happens for like two reasons. If they are placed very closely, right? So at that time, when one signal has fast switching or high frequency, these both will have a capacitive coupling. Coupling means like when a current or energy goes from one circuit to another, it is called coupling. So why is it called a capacitive coupling? So it is like a parallel plate of two capacitors, right? So when there is high frequency, the signal will like switch from this to this, like bleed here. I mean, not fully switching. Like field will be going through here only, but there will be mm, like transfusion or expansion of field over here as well. Why do that happen? So in PCB design or anywhere in the world of electronics, signal always moves through the path that has the least impedance if it is not DC. So impedance, you should have heard it in AC, right? So in this high frequency state, least impedance will be there when when the frequency is low for the capacitor. I mean, the frequency is very high for the capacitor. It's 1 by omega C. So omega is high. The total impedance of the capacitance will be low. So this will be more prone to be going to this state when the impedance is low instead of following this resistive path. So it will be a competition between resistance impedance and capacitive impedance. We should see to that doesn't happen. And the second thing is the inductive coupling that can happen when they go for a long distance. What can happen is when there is a current spike and all, there will be a voltage spike. There can be signal transfer when there is a current spike, because if you consider this as a one inductor, this as the other inductor, any current carrying thing, the voltage drop or happening here will be mutual inductance times the current rate, right? So the magnetic field will be always present between these two, but when there is a voltage spike, I mean current spike, there can be a voltage spike over this signal trace also. So how do we avoid that? We only have a standard thing called a 3W difference. Keep these two traces at a difference of 3 times the width of each trace. So how much is this? 1.1. And this trace is 0.254. It is already greater than 3. So that is how we avoid the crosstalk. We cannot completely avoid it. We can avoid it to a great extent by this method. While going through while tracing out, we'll see what are the other possibilities of noises and how can we ignore them. Not ignore them, avoid them. Like handle them perfectly. So do the signal traces first and see how much areas left for you to do the VCC. see that this axle length one cannot be connected to this directly. So we'll use wires in that case. First, we'll do these connections fast. So there will be a conflict here also. We won't be able to do one thing. So I'll go with this. This is fast. I mean, this is should may the signal part, if it is like less congested, the routing will be very easy. What else? Okay, this. We completed the signal part. So for we have left spaces for ground and VCC. Now I'm going to tell you another concept. Like the thing is, EMI can be transmitted as radiated EMI or conducted EMI. Like there's a minimum chance of conducted EMI in this case, where two signals like have a common point, like the example power rails, VDD or GND, and noise from one another is getting captured by the other and goes on. The radiated part is what we'll need to focus on more. The thing is, the traces, the radiated EMI is when the signal gets transmitted like EM waves to other signal or trace. This can happen when we have antenna-like structures. So if you focus this, if you have long traces comparable to the wavelength of wavelength of the RF range, RF is radio frequency range. So at that point of time, the trace will act like antenna, and it will transmit radio frequency, the signal as a radio frequency to other parts. So if another signal is able to capture this RF or EM waves, then it will be able to capture the noise, and it is unintended and it affects the circuit operations. So that is one point. And the second point is another antenna-like structure can exist with us. That is the loop area part. As explained before, the loop area is when you have a closed loop and they can act as a circular current carrying. You should have learned that magnetic field passes through the axis of a circular current carrying conductor. So what happens is, if you have a closed loop and if it is considerably large, there is a high possibility that EMI is radiated from the loop as changing magnetic field, which causes a changing electric field as EM waves. And if there is any other part that is viable to get the radiated EMI, then it takes it as noise. So these antenna-like structures, the long PCBs and also the large loop areas, they act as antenna for radiating EM waves and also for receiving them. So EMI is more prone because of those structures. We need to avoid them as much as possible. So a loop is what? A loop is when it starts from the VDD itself, the VDD to the internal circuit to the ground and goes to the ground of the ESP32 and goes to the ground of the regulator or the power supply. So this is a big loop only. So how do we reduce that? We don't connect the ground again through traces to the ground here. That will increase the loop area. So what we'll do is we'll have a ground plane beneath the signal trace so that the EMI, so that the loop area becomes small. And even though the forward current path may be considerable, the width of the loop may be small so that the total area is small, and EMI, the radiation or the noise from the circuit is less. It doesn't radiate as an antenna structure. That is the point. So the second point I wanted to tell is, if you want to route the VDD part also, we can do them in the bottom layer. There's space there. We did almost all the signal traces connection except two of them. If you want to do the VDD traces, we can do at the bottom, but that also increases the loop area. We should minimize the loop area as much as possible. And there's a thing you must keep in mind, that a 2-layer PCB has the same thickness as a 4-layer PCB. So the thickness of the PCB does not change if you change the layers. What we'll do is we'll keep two more extra layers, in 1 and in 2, where we'll keep ground plane here and VDD plane. Why we are not using, we can also keep the VDD plane in the top layer and ground plane in the bottom layer. Why we are avoiding this, that type of configuration is because when we keep the VDD plane in the top layer, what happens is the decoupling capacitor is completely ignored. The plane will cover the VDD part directly. It will also cover this, but there will be no point if it is directly connecting to the VDD part. And that is one reason. And the second reason is, having a plane does not reduce your loop area. It still has to go through all these signals, travel all here and go here. And if you keep the plane here, it has so many obstacles, and the loop area still is high, and inductance increases, impedance also increases, the radiation also is high. So we don't want those things. This is a GPS module, and LoRa also, those are highly sensitive. I don't want any noise in my circuit. So I'll go with 2 more layers. Go to inner one, place the ground pore, a copper pore with net ground. Yeah, so go to inner 2 and place VDD. I hope the reason we are placing these 2 layers is clear. Like, we can also do it in 2 layers. The routing will be completely easier and within 2 layers also, but our goal is to reduce the EMI as much as possible. Because signal traces were almost completely done in top layer itself. The problem is not routing, the problem is with the EMI. So now come back to your top layer. The thing is, now these are SMD pads. They are not through holes. They won't get connected to your ground or VDD plane automatically. We need to make efforts to connect them. So what do? We have to use wires. And also the power rail must be of higher thickness or width than the normal signal traces. Make sure that happens, because there will be a high amount of heat generation as more current is possible. So how do we? Okay, see, this is how we will connect the wires with. We can directly place a wire here, but to show that we can we are placing a wire and not using a through hole. I'm placing it over here. Similarly, connect everything. These are decoupling capacitors. Connect this here. Don't connect them directly through wires. What is happening? Oh, okay. We keep on doing that. For decoupling capacitors alone, connect these traces to decoupling capacitors and then connect wires to through decoupling capacitors. That is the whole point of using a decoupling capacitor. If you don't use them, there's no. See, in these type of devices, like there will be multiple grounds. Why are they present? Sometimes the devices, even if they have multiple grounds, they won't be like shorted among themselves. And in some devices, they'll be shorted. If they are shorted, these grounds are used for getting more current when the process is getting hectic. But if they are not shorted, then these grounds are for different purposes. This may be a digital ground, this may be analog ground, this may be a power ground. So there will be different purposes we assign the grounds for. So that is the reason we have sometimes multiple grounds, multiple VCCs and all. So here we can't use the 0.6 mm width. This is too small, so we'll use a 0.254. It doesn't matter much because it is too close here. Like we can connect this to this VDD to this VDD, but we should not do that because if this has a voltage spike and this VDD level goes below 3.3, and this is like noise free within the internal circuit, this will also affect this, and this also goes to less than 3.3 without any reason. So it is better to have separate wires connecting them to the VDD planes. That's it. Now place all the wires. V is the shortcut hotkey for wire. The thing is, if you want to have a wire, make sure that it has the same net as the one we need to connect to, or else the trace won't get connected. Now we have placed wires, right? There will be, if you see them clearly, these are the copper areas, and this is the wire, the ground plane and the VDD plane. These are the wires. The copper, this is the copper of the wire, and this is the copper here. Both are touching, and there is no clearance. So we should make some clearance. If this wire is for G and if this wire is for ground and this wire is for G and D, the ground plane should not make contact with this. So we need a clearance. So what we'll do is touch this, rebuild copper area. Now you can see some gap is there here also. The clearance is 0.254 millimeter. It's actually the default value, a good value, and it's also equal to the trace width. Now we go back to top layer, or we are already in top layer. Wow. We need to make 2 more connections, and why? Okay, we are seeing these things, right? These are called the thermal wires. You should have. Satvik had explained this in the third session. These are thermal wires for dissipating heat, and these pads are for making the surface distributed to make the heat dissipate through a larger area. So first we'll check our DLC. 30 errors. So these 12 and these 12 are coming from this. I'll deal with this shortly. So there are incomplete connections. Oh, Okay, I not place a wire here. Okay, this is the one we need to connect. Let's deal with this later. Here also wire missing. What happened here? Okay, not place anything here. This thing is not getting connected. See, because the net net of the wire is not specified. Only if the pin and the pad or the wire has to have the same net for them to be connected. Now see C and D. Only it gets connected. So make sure that you have the same wire with the same net. Next is this thing. That also we need to do it in the bottom layer. Again, we'll do check DLC. DLC is for like the errors we need to make sure they don't occur so that the manufacturer, so that we get the product without any disabilities, defects, anything. Okay, the clearance. We did not rebuild the copper area, right? That clearance. Every time you do this, rebuild the copper area. That is important. Then 26, 24 are from this, and 26 is from, and the two more are the incomplete connection. So we'll see how we can. Okay, I want you to know why there is these DLC errors. What are these DLC errors? Design rule errors. So go to this design rule. What is this for? So every FAB, FAB means the manufacturing company that makes the PCB. We'll design the PCB in this simulator. We'll give it to the manufacturer and he does the manufacturing, right? So the manufacturer will have a default value of track width clearance that we should maintain in the PCB layout so that the PCB that we get back is not defective, no much of interference happens. Everything is made sure that everything is perfect when the PCB arrives to us. We should like match with the manufacturer's capabilities. If you want to see how to get the manufacturer capabilities, go here, ALC PCB manufacturing capabilities, and you'll get to see it over here. We are going for rigid PCB only. And you will see over here drilling traces, drill diameter, everything is over here. Available open source for us to know what we should do, what values we should place it here for for the specific manufacturer. So according to the manufacturer, if we have to use the design rule, and if our PCB layout has some mismatches while routing or placing wires, the design rule check will put forward those things. So what are these is that the wire diameter and the hole size is small. So what we'll do, we'll increase it. That's it. Increase it to how much? Minimum 0.61. We'll put 0.62. And this to 0.31. Okay, what is this copper area? Exposed copper area. If you press this exposed copper area, then in the solder there will be a solder mask above this layer, top layer, right? In that you can see the copper area around this wire. It can be used as a test point with the multimeter. If you don't want to have this wire to get the interference from externally or keep protected the copper layer and avoid unnecessary metallic contact, we can leave this untouched. So do it for other wires as well. 0.62 and 0.31. if you do so that the design rule is matched, you are safe and the PCB is also good to go. Okay, you see, right, the pad and the PCB wires are making contact, but it won't raise error. Why can anyone? Okay, no one is. So it is because that both the wires and the pads are having the same net. Means they are already having a contact with each other. They want a physical contact with each other. That is already made. If it is like overlapping or not overlapping, it doesn't matter at all. It will not raise an error because both want to get connected to the same net, that is ground. Like there are 12 wires, I guess. So it takes some time. Just do it. Not only in these thermal wires, but also in any wires and pads that have the same net, right? We can overlap them. We can also place this wire directly above it. But since it is part of the footprint of the ESP32, I cannot like change the wire placement. I cannot shift it over here and all. They must be kept at the same place. They cannot be shifted, first of all. You'll see the DLC levels reducing to 2 when we complete this. The 2 is for incomplete connection. Where should we do signals? Okay, I forgot to rebuild the copper area. Man, you should like remember this thing to rebuild the copper area to have some clearance. Signals. Yeah, we got as expected 2 only. How are we going to connect this? That is simple. Use wires. Place a wire here. Place a wire over there. Why do we need 2 wires and not 1? Because these are pads. If one is a through hole and other is a pad, one wire would be enough. Because 2 of them are through holes, 2 of them are SMT pads, the wiring should be done only at the top layer. It cannot be done at the bottom because the pad is only present at the top layer. I hope you get it. Before that, I'll reduce the... Okay. Oh, the wire should have the same net. What is this net? Axle into 1. Copy this thing. And place it over here. You'll see a rat's nest line or rat line coming over here. If you don't see that, then it has a different net. Why should we make sure that they should have the same net? Only if they have the same net, they will be going to the layer where we want the connection to, or they'll be connecting to this pad we want the connection to. Actually, in ECEDA, what happens is any wire we place, it will go through multi-layers. It will go through all the layers. But in Altium or KiCad, if we want, we have to specify the layer we want. It is like in ECDA, it goes through all the layers. So we need only thing that separates is how that separates which layer we want this wire to be connected is by keeping the net. That is the importance of net to a wire. I hope you understand. Okay, we'll be doing this connection at the bottom. And this also. This is SPI MOSI. Okay, that's it. We go to bottom layer. There will be only 2 connections to make. The thing is, we could have made the VDD connection here itself. But why didn't we make it? Because if we make it in the we can't make it in the bottom layer because the SMD pads on the top layer. Only we can make the connections in the top layer. Why we didn't use the top layer for VDD connections is because we don't want larger loops. If we have large loop areas, then the EMI interference is prone to occur at a high rate. We want to minimize everything because we are using a LoRa. It's a weak signal, though it goes for a long distance. We go to the bottom layer and do the connection. That's it. We are done. W. Oh, the copper area. Okay. The thing is, whenever we do the wires, we build your copper area. There should be some clearance. That's it. So we'll change this border outline. The thing is, you see that I don't care about this, where this, what are they called? The planes exist. Even if they exist over this whole window, I don't mind because in the board, it only occurs inside the board outline. So go to tools, set board outline. It already sets it for you based on your component placement. Okay, I don't want this much also. Okay, the top part, there is some extra space. So what we'll do is remove them. Or it would be better if I do this thing ourselves. Sometimes it works. It like perfectly does the border outline for us. Sometimes it goes through the plane for us. So go to the border outline part, W, and then do. This is the final part. You put this 3D model invisible, and this is what you'll get at the end. Let's see what we can do next. Display prefix. Okay, see if you saw right, the prefix are coming over here. Sometimes it is like congested. I don't want them to exist. Put this display prefix to no. Be better. Sometimes it is like important. That's it. Okay. So this is the design rule. First, we have to make sure that the design rule is based on the manufacturing capabilities of the rigid PCB. Then you already have this schematic. You just what do you do? What do you do? You just go to design and convert schematic to PCB, and that's it. You're done. What if after doing some part of the PCB, you want to introduce another component? You can also do that. Place a symbol here. Let's say don't non let's say common library itself. The components here are getting prefixes R7 and R8. Sometimes they will be named as R question mark, R question mark instead of R7 and R8. In that cases, what you should do is go to edit, annotate, and keep existing annotation if you have already done some part of PCB connection. Why? Because if the prefixes change, right, then what will happen is the connection will also get like confused. It will like get disconnected if the prefixes are changed. If you do re-annotate all based on the directions, the rows, first it will see all the rows. Keep the top ones as 1. This will be R1, this will be R2, and goes down below. If you keep columns, it will go name in this way. R1, this will be R2. This will be R2, this will be R3, like that. That is the purpose of annotation. If you don't give this annotate when there's a question mark, there will be 2 components with the same name. Then it will give a design check, design rule check. What else can be told? Cross probe we saw, right? If we want to know exactly where this component is there in the clumsy PCB layout, go to tools, cross probe, and then click on this design, convert schematic to PCB. That's the only thing. This view, you can view this is the left hand panel, this is the right hand panel, drawing tool, wiring tool. The preview window is not much of importance. It will just be there. This is the historical record. Whenever you save a layout or thing, you will see this. And when you give this and recover, you'll go to that PCB layout or your project file. This will be overwritten. If you have made a mistake, you have to do that. That's it, I guess. Did I miss something? Okay, these are for aligning left and right. This is for rotating. So instead of rotating, we use space bar, space. I guess I have completed. Okay, if you want to know what are the shortcut keys, you can go to the settings, view shortcut keys. I hope. Okay, we need to know attendance. Scan for attendance. Right, we'll wait for 3 minutes. Yeah, we'll see few things. Why DLC occurs? It occurs because of clearance, unconnected nets. Unconnections is very, like, you can by intuition itself understand that if the traces are not connecting the pads we want the rat lines exist, then it arises board outline issues. And there's no board outline, these small issues occur. And the drill or wire issues, it's very important. Like if the manufacturer wants the wire you simulate to have this drill size, this much drill size, this much copper area, this much annular ring. Annular ring is the uh, distance between the rings formed between the drill and the diameter of the wire, the full diameter of the wire and the drill. These all must be in correct, I mean, at least in the minimum measurement the manufacturer provides us. And the clearance, the traces and the pads should not be too close to each other. Wires and the traces should not be too close to each other, and so on. And the copper core and the signal wires. This was the thing we were rebuilding copper area for. That is all that is here. So I wanted to show you like the island formation I just told, right? What is the island formation? So when when this layer is done in within 2 layers, it can be done. Like this is a good thing. This was done in 2 layers only. But sometimes when we want this happens, if I had made the VDD plane to be like this instead of getting cut over here itself, this would have gone till here and the connection would have gone. But what is the problem is, if you do that, it would be fine. But the copper area length, the length of the loop will increase. That is the reason we use 4 layers. Here is what the island looks like. See here. It doesn't have it doesn't have any space to go and meet the other part of the VDD plane. So it just gets sticks here. So this part is completely isolated from here. So VDD and this VDD are not even connected at all. This is how the GND, I mean, the island formation looks like. This is an island. The thing is, I wanted to show how an island looks like. This if it is the polygonal plane, if it is like made like a square over here instead of a cutout portion, there wouldn't have been any island. But the length of the loop would have increased, and inductance and impedance would have increased a lot, and interference would have increased. So that is the reason we put a 4 layers. I hope it is clear. That's it. Amazing.
We can end the session, right? Tejas, can we end the session?
Yes.
Yeah.
Devesh is host, I guess. We can't end ourselves. We have to leave, I think.
Okay. Yeah, guys, this is the end of the summer school, and you can post your doubts in the group discussions. We'll try to answer everything, and do listen all the sessions and try to cover up everything and simulate on your own. Thank you, everyone.